So today we're going to review the material that we talked about last in class, and that was valence electrons. Remember that these are the electrons found in the very outermost energy shell. And I'm just going to show you a very basic diagram of an atom to show you where those valence electrons are. And first, just to show you or give you kind of an idea, let's talk about carbon. Carbon has 6 protons and 6 electrons. That's the neutral form of carbon. And if we did the electron configuration for it, it would be 1s2, 2s2, 2p2, right? So that equals 6 electrons. What I want you to notice first is that these numbers here kind of refer to those energy shells. So this is the first energy shell, and it can only hold one orbital, so it can only hold 2 electrons. The following orbitals, or the following shells, can hold up to 8. So if you look at the s orbitals, you've got 2, and then you've got the p orbitals that have a maximum of 6. So total that equals 8. But let's just look at carbon real quick. So I'm going to draw that first energy shell that has 1 pair of electrons, so that's the 1s2. And then the second energy level has 4 electrons. Now, keep in mind that you don't pair them up until you have all of the singles in that energy shell. And that, remember, that is Hund's rule, where you don't pair them up yet. So if we're looking at all of the electrons in that second energy shell, we have 4. And so here's 1, 2, 3, 4. Carbon has a valence number of 4, meaning the very outermost energy shell has 4 electrons. So if I was going to ask you how many valence electrons does carbon have, it has 4. If I asked you how many electrons carbon has, it has 6. But remember, those first 2 are in the innermost energy shell, and then the outermost has 4. Let's do another one real quick, just to kind of solidify this concept. Let's look at sodium. That's Na. The number is 11, and if we did the electron configuration, it's 1s2, 2s2, 2p6, 3s1. So, and I'm going to draw this one a little smaller. So here we have sodium, and I'm going to show you again very basic diagram. So the first energy level has your 2 electrons. Second energy level has 8 here. This is 2s2, 2p6. So that's 1, 2, 3, 4, 5, 6, 7, 8. And then we have 1 more electron that's in the third energy level. So if I was to ask you how many valence electrons does sodium have, you should only be looking at that one last electron that is in the third energy level. So its valence number is 1. Now, I'm going to show you how you can do how you can determine the valence electrons from electron configuration, and then I'm going to show you how to do it from the periodic table. So if you do the electron configuration of arsenic, let's take that is As, and it is number 33. Okay, sorry about that. So we have 1s2, 2s2, 2p6, that equals 10. 3s2, 3p6, that's another 18. 4s2, and then we do 3d10, and 4p3. Let's just make sure. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 3 is 33. So we've got our 33 electrons. Okay. Now if I want to determine the number of valence electrons just from the electron configuration, I can do that. because here I want to look at where are our outermost energy levels. So we're looking at these numbers here because these show you your energy levels. So the 1 in the front of the orbital type, the 2 in front of the S, the 2 in front of the P, those are energy levels. So we're looking for the ones that are on the outermost. So we've got 4 here that are the outermost. So in this case, I'm going to add up all of the electrons that are in the 4th energy level. So here you have 2, here you have 3. So arsenic has a valence, has a valence of 5. You add them up. Notice that even though you have the 3d10 in between the 4s and the 4p orbitals, the 3d10 electrons are actually closer to the center than the 4s electrons. And that has to do with how the electrons then backfill some empty spaces in the previous energy level. It's a little bit more than I need you to know. Just remember that you're always looking at the s and p orbitals to determine valence electrons. Now, there's an even easier way to determine valence electrons, and that is from the periodic table. So this is the periodic table that is in your textbook, and I know it doesn't fit completely on the screen, but I think you'll get the picture. Okay, so notice that your periodic table is numbered by groups. Okay, so the vertical columns, those are called groups, or they're called families, so either way. Now, this family here, this very first column, has a 1 on top of it. Conveniently enough, every single element in this column has only 1 valence electron. For this column here, has a 2 on top of it. Again, conveniently enough, every element here has 2 valence electrons. Now we're going to skip to the P block here, because remember, when we're determining valence electrons, we only use the s and p orbitals. So the group that starts with boron, the top, all of these have 3 valence electrons. Now I know this is group 13, but if you just ignore that 1, you can remember, okay, there's 3 valence electrons in each of these. Carbon's group has 4, which we saw. Carbon really does have 4 after we drew it. Nitrogen's group has 5. Oxygen's group has 6. Fluorine's group has 7. And helium's group has 8. However, helium does not have 8 valence electrons. It only has 2. The reason that helium is placed above these other elements, and all of these are called noble gases, is because it behaves in a similar way to all these others. And the reason for that is that helium does have a completely filled outer energy level, or outer energy shell. Just remember that that very first energy shell can only hold 2 electrons. So since helium has those 2 electrons, it's done. It doesn't want any more. It doesn't want to lose any. It doesn't want to gain any. It's perfectly happy. It's a very stable element. As are all of these. It's just that neon all the way down, they have 8 valence electrons. Now, the whole D block here and the F block here, they conveniently all have 2 valence electrons. So keep in mind, we only look at the s and p orbitals for valence electrons. So all of these have s2. So every element in this period right here, going from scandium to zinc, has 4s2. And then it has 3d1, 3d2, 3d3, and so on, but they all have 4s2. So those final 2 electrons, or those 2 s electrons, are the valence electrons for all of those. Same is true for the rest of the D block and the F block. Now later on we'll look at some elements that can be a little different depending on what other elements they are near, but for right now, the thing that you should remember is that they all have 2 valence electrons. Okay. Now, I want you to also know about the octet rule, which we kind of just went over, but I want you to know what it's called. Octet rule. Okay, so oct means 8. So the whole point of the octet rule is to kind of remind you that all atoms want 8 valence electrons. All atoms want 8 valence electrons. So what some of them are going to do is they might lose an electron or 2 or 3 in order for their outermost energy shell to be completely full. So if you've got sodium, which had 2 in its first energy level, then you had 8 in its second energy level, and then it had 1 in its third energy level. Well, I want you to realize that sodium really wants to have a completely full outer energy level. However, it doesn't. It has this 1 energy level with 1 electron, so it's stable, but it really wants to have 8. So you have to consider, okay, is it going to be easier for sodium to add 7 electrons so that it can have 8 in its outermost? Or is it more likely for it to lose one of those electrons? And the answer is that it's more likely to lose one of those electrons. So if sodium loses that electron, notice that entire energy shell is now completely empty, and now it has 8 in its outermost energy shell. Granted, now sodium, which normally has 11 protons and 11 electrons, now has 11 protons and 10 electrons because it just lost 1. And so if that's the case, then now sodium has a charge, and the charge on that sodium is a +1. So watch the next video and I'll talk a little bit more about charges so that it kind of ties everything in.